Hello, everyone. Welcome back. My name is John Morrow. I'm a professor of material science and engineering at Penn State, and I've got something a little bit different for you today. We're going to be taking a look at the underlying physics that governs workplace accidents. Specifically, what is the probability of workplace accidents happening at different time durations? We're going to discuss this in terms of a physical phenomenon known as self-organized criticality. First of all, why do we care about this issue? Workplace accidents are actually rather prevalent across the United States. Back in 2015, according to the Bureau of Labor Statistics, which is part of the U.S. Department of Labor, there were nearly 3 million workplace accidents reported in that year. Almost 1 million of them were lost time accidents, meaning that the workers had to miss some work, whether it's one day, a week, or more. Some of these accidents are, of course, just minor accidents like cuts, but they could be as severe as, major accidents that end people's careers, or even worse yet, fatalities. Here in Pennsylvania, about 3.5% of workers have experienced a workplace accident in a given year, and it's pretty similar statistics across the country. So it's really important to understand what is it that governs workplace accidents and how we can help prevent them going forward. Now, the physics that I would like to draw upon is due to a Danish physicist named Per Bak. He lived from 1947 through 2002, and he invented this concept of self-organized criticality back in 1987. This was introduced in his famous book called How Nature Works, The Science of Self-Organized Criticality. This is a theory that finds a common underlying physical origin of many different phenomena that we see in both physics as well as in biology and even in the social sciences. This is a quote that was published in this article in Nature that the theory of self-organized criticality spread like the forest fires it describes through the scientific community, and his ideas were adopted around the world. Perback, in addition to being known for his work in self-organized criticality, was also known for his, quote, lively temper, which was legendary. Woe betide that seminar speaker who had misunderstood a central idea or happened to find himself at cross purposes to it. So quite a lively character. I never had the pleasure of meeting him, but his legacy lives on through his theory of self-organized criticality. Now, when Beck first introduced this theory back in 1987, the case that he considered at first was a sand pile model. He considered, what if you drop one grain of sand at a time into a sand pile here? So you've got a sand pile that gradually builds up one grain of sand at a time. Now, most of the time, the grains of sand as they fall will just sort of build up and the pile will grow bigger, but occasionally dropping one grain of sand will induce a landslide to form. So it will cause the grains of sand to help slide down the sides. And if you measure the size of the landslide in terms of either the number of grains involved with a given landslide or the mass of the sand that is involved with the landslide, if you measured that size of the landslide in terms of the frequency of occurrence, that is described by what's called a power law distribution, which is shown in this equation here, where n is the number of events of size x, and the number of events of size x given by this power law distribution is described as equal to a, this pre-exponential factor, times the size of that event x raised to some power minus k, where this exponential factor here, k, is an indication of the average size of the events. And what this means is that if you take the logarithm of both sides of this equation, or in other words, if you plot it on a log-log graph, as shown here on the right, and Beck's article from Physical Review A, 1988, what we can see is that the size of the events here on this log-log scale is following this straight line distribution here. And the slope of this plot gives you k, gives you this factor here, minus k. And the underlying assumption here in self-organized criticality is that all of these landslide events have the same underlying cause. They're all caused by a perturbation of one of these grains of sand falling in just the right way to induce some landslide event. And it doesn't matter if it is a small landslide or a large landslide, they all have the same underlying cause. This is the principle of scale invariance, that it doesn't matter if it's small or if it's big, it has the same underlying cause. What's different is the frequency of events, and much smaller events, in other words, smaller landslides, occur exponentially more often compared to larger events. And that distribution is described by this power law here. Now, Purbach's theory of self-organized criticality doesn't just describe this distribution of landslide sizes in a sand pile. It has been applied across science. Earthquakes are another canonical example of self-organized criticality. Earthquakes are all caused by the same underlying plate tectonics, right? And earthquakes are occurring all the time around us, but most of them, the vast majority of them, are so small that we don't even feel them. If you plot the size of the earthquake or the magnitude of the earthquake versus the number of earthquake events, again, you will get the power law distribution described by self-organized criticality. Forest fires are another example. If you plot the frequency of forest fire events as a function of the size of the forest fire, for example, as measured by the number of acres of forest that are affected, again, it follows a power law distribution. Disease epidemics. So if you measure the number of people affected by an epidemic versus the frequency of the epidemics, again, a power law distribution. Financial markets like stock market crashes, same thing, power law distributions. The underlying statistics of social networks, wars, and so on. Time and time again across both the hard sciences and across the social sciences, self-organized criticality comes up. And what this is saying is that there is a scale invariance here with respect to small events versus large events. They all point back to the same underlying cause, and the frequency of those events follows this power law distribution. So how do we apply this to the science of workplace accidents? What we did was to gather all the data from the Bureau of Labor Statistics about the number of workplace accidents measured as a function of the severity of those accidents. And we're measuring that severity in terms of the number of days that the workers have missed work. And if we plot this on a log-log axis, on the y-axis here, we've got the number of cases expressed on a logarithmic axis versus the number of days missing work, which is a measure of the severity of those accidents. You can see this straight line here on the log-log plot. So this is following a power law distribution. If you fit this to the power law, the number of accidents here is equal to this pre-exponential factor times x, the severity of the accident, so x is the number of days of missing work, raised to this power here, minus 1.014. And this R squared factor shows you the goodness of fit of the power law to the data, and the R squared of 0.9773 means that there's an excellent goodness of fit of the power law distribution to that data. So this is looking at workplace accidents as a whole, and the great fit here to a power law is evidence of self-organized criticality governing workplace accident statistics. But let's look at a little bit more depth here. If we separate the workplace accident data by work sector, here in the first column of the data, we have the different sectors of industry here, from goods processing, natural resources and mining, agriculture, forestry, fishing and hunting, construction, service providing, utilities, and so on. We fit all of these data for each of those individual sectors to the power law distribution, getting the pre-exponential factor here A, the exponent here k, which governs the average number of days of the workplace accident, and then the R squared fit, which is the goodness of fit. And what you can see if you look down all the rows of the R squared data here is that the R squareds are all above zero point 0.9, and most of them are very close to 1. And so regardless of which sector we're looking at, from all of these independent data sets, they all follow a power law distribution. So there's evidence of self-organized criticality, not just looking at the totality of the workplace accident data, but even if we go sector by sector. And the different values of K here indicate the average number of days lost from work. So let's take a couple of examples here. In the plot on the left, this shows the number of workplace accidents as a function of the number of days missing work in two different sectors. The lower plot here in gray shows management of companies and enterprises, and the upper plot shows the service providing sector. You can see that the slopes are almost identical, and that's reflected in the exponents here being almost identical, minus 1.026 in service providing sector and minus 1.02 for management of companies and enterprises. And what this means is that the average number of days missing from work is effectively the same across these two sectors. The only difference here is in a vertical shift, and that vertical shift is just due to having a much greater number of people working in the service providing sector versus the number of people who are working as management of companies and enterprises. Over here on the right, you can see examples where we've got two different slopes that appear. The upper line shows the arts, entertainment, and recreation sector. You can see that this has a higher exponent, so it's minus 1.147, versus mining, which has a lower exponent, minus 0.761. And this lower exponent actually indicates a greater average number of days missing work. And what this is showing is that even though both of these do follow the power law, they both show evidence of self-organized criticality. In the case of mining, the accidents on average tend to be worse compared to the accidents that occur in the arts, entertainment, and recreation sector. So they both follow self-organized criticality, but on average, accidents in the mining sector tend to be worse than most other sectors. But the overall conclusion here is that the power law scaling is observed in all sectors, which is pointing to the self-organized criticality governing the physics of workplace accidents. So what does this mean from a practical point of view? This actually provides evidence for something called the Heinrich accidents triangle. And what this is arguing is that to reduce the rate of major accidents and fatalities, a workplace culture must be advanced that addresses unsafe behaviors and attitudes, so that by reducing the rate of minor problems, the major accidents can also be avoided. The idea with this Heinrich accident triangle is that we have unsafe conditions or unsafe practices that form the basis for why do workplace accidents occur in the first place. So this is all about the safety culture of an organization and whether they put a lot of value onto workplace safety, whether they provide proper training, whether they pay attention to small infractions, and so on. And if you have a culture that has unsafe conditions and practices, that makes it more likely for workplace accidents to occur. The workplace accidents that are most likely to occur are the minor ones. So, for example, if you have 300 non-injury errors, so just sort of 300 near misses as a result of unsafe practices, an accident could have happened but was missed, fortunately. For every 300 of those non-injury errors, almost 10% then would actually have events that lead to minor injuries. These would be like cuts, scrapes, just sort of minor accidents that may occur. And then for about 29 or 30 of those, you would have one major accident. And this, of course, is the thing that we must avoid at all costs. This is where you've got some major health issue that results from these accidents for an individual that leads to not only lost work time, but it could lead to permanent problems as a result of the accident, or worst case scenario, even fatalities. And all of these go back to the underlying unsafe conditions and practices. So for every one major accident, there's about 29 minor injuries. And for each of those, there are about 300 non-injury errors. And all of them have the same underlying cause, which are the unsafe conditions and practices at the workplace. So this analysis through self-organized criticality is providing evidence in support of this Heinrich accident triangle, because all of these, whether it's a major accident, a minor accident, or near miss, they all point back to the same underlying cause, which would be a culture that doesn't value safety. And so if we want to prevent these major accidents, what we need to do is focus on the culture of the organization, make sure that workplace safety is stressed, and make sure that everyone pays attention to the minor issues. If we pay attention to the minor issues, that will also suppress the frequency of major accidents. So thank you for listening. If you wish to learn more, you can check out our paper on this topic. It was published in 2018 in Physica A, which is a journal devoted to statistical physics. This was work done together with my co-authors, Brett Deal, who was a student at Penn State at the time, and two of my colleagues from Corning Incorporated, Rich Marcellin and Dan Vaughn. So thank you very much for listening. If you'd like to share any comments, feel free to drop them below. All right. Thanks, everyone. I'll see you next time.